Hello everyone, my name is Fei Fei, and I'm Professor Jean's personal assistant. It's a pleasure to guide you through today's presentation on smoothie, our computational tool for non-elastic breakup calculations developed on the basis of the Ikemura-Austern-Vincent formalism. And, if you will do note our affiliations with Tongji University and the University of Seville, as collaboration truly lies at the heart of this project. Moving on to the outline, I'll first explain why breakup reactions matter, then classify the different breakup scenarios, introduce the IAV model, and show how smoothie implements it. After that, we'll walk through the installation, the inputs, the outputs, and highlight 3 applications before closing with a summary and acknowledgements. Please keep this roadmap in mind, as it closely mirrors the structure of both our documentation and the paper. On the next slide, we discuss reactions involving a turbidity-structured projectile, such as a halo nucleus or lithium-6, modeled as an alpha core plus a deuteron cluster. When such a projectile collides with a heavy target, multiple direct reaction channels can open within a very short interaction time. Elastic scattering is one possibility, which we use to extract optical potentials, root mean square radii, and density distributions. Asyncline nucleon transfer is another, providing insights into spins, parities, and spectroscopic factors. Breakup is the third key channel, allowing us to probe the nuclear dynamics and the structural fingerprints of weakly bound systems. These channels are categorized as direct reactions since they occur over a short time scale and involve changes to only a few degrees of freedom. In contrast, many body reaction channels such as fusion, followed by evaporation, play a role in stellar energy production and nucleosynthesis. Therefore, breakup reactions occupy a central role. They simultaneously encode dynamical information and reveal the intrinsic properties of weakly bound projectiles. Now, let's classify breakup events. There are 2 categories to keep in mind. First, the fully measured case hex. We detect every outgoing fragment in coincidence, sometimes including accompanying gamma rays. That level of detail enables complete kinematic reconstruction and very fine, triperichal cross-sections. The payoff is excellent structural insight. The cost, however, is demanding experiments with complex detector arrays and relatively low event rates. On the theory side, sophisticated few-body methods are typically required to track all final state interactions. Second, the inclusive case heck, we detect just one outgoing fragment, and we integrate over everything. We do not observe. The observable is a doubled efferential cross-section. Application 2, reported versus angle surrogate and reactions. For that detected uranium-2, we will detail the contributing pathways and the formalism proton on the upcoming Here, slides. Inclusive breakup to anchor that distinction, neutron-induced cross-sections on short-lived nuclei where every populating compound state. Within this exclusive category, ability to there are 2 subchannels, doubled elastic breakup sections, where all participants for evaluating their ground surrogate experiments, and inelastic breakup, where one or more fragments, or the target, ends up in an excited state. You can point out how this channel demands complete kinematic reconstruction. In contrast, the inclusive lithium-6 example on the following slide detects only one fragment, leaving the partner unobserved. Smoothie is grasped for these inclusive scenarios, integrating over all the unmeasured outcomes, while the unobserved fragment interacts with the target. In the more common inclusive case, the focus of smoothie, we detect only one outgoing fragment, and we integrate over everything we did not observe. Measured quantity is a doubled ferrhodential cross-section versus angle and energy for that detected fragment. On this inclusive breakup slide, please note the possible reaction pathways that can contribute to what we measure. Elastic breakup, where all participants remain in their ground states. Inelastic breakup, where one or more participants finish in excited states. Incomplete fusion, where one fragment fuses with the target and forms a compound nucleus, and transfer processes which move nucleons between the projectile and the target. In our terminology, the combination of inelastic breakup and incomplete fusion, is referred to as non-elastic break-ups. Within the Ikimura-Ostern-Vincent framework, this sum over what we did not see is handled analytically. Using a Green's function for the unobserved fragment moving in the target's optical field, this produces a clean separation between the elastic breakup piece and the non-elastic breakup piece. Inclusive measurements are efficient and widely used, but they are historically hard to calculate because the space of unobserved outcomes is huge. The IAV formalism provides the needed mathematical closure, and smoothie implements the finite-arranged prior form version to make these observables practical and reliable. Before we dive into the equations, let's pause at the slide titled Study of Inclusive Breakup. We present 3 use cases in this order. First, the inclusive spectrum. In lithium 6, you see a clear alpha band dominating, which strongly suggests that non-elastic processes are contributing. Second, the surrogate reaction. Here we study the compound nucleus, focusing on how it is formed and how it decays. In particular, for the case of a neutron-induced reaction on a short-lived target. In such cases, neither the neutron nor the short-lived nucleus can practically be made into a target. So, the surrogate reaction becomes necessary. One can use a deuteron as the target and study the interaction of the short-lived nucleus with the neutron inside the deuteron. Third, the knockout reaction. We use it to extract spectroscopic factors. Most analyses rely on the econal approximation, but first, one needs to examine this approximation using a fully quantum treatment. And indeed, a fully quantum treatment is needed for precision. Smoothie provides the observables for each case, so this slide serves as your rate from measured spectra to physics conclusions. Now we arrive at the theoretical engine, the Ikimura-Ostern-Vincent model. This is a fully quantum mechanical description of breakup. On the slide, you can see, first, the inclusive breakup definition, thus a plus A goes to B plus B star, with it equals B plus X. Next, the non-elastic breakup cross-section. It is proportional to rho sub B, multiplied by a matrix element of the imaginary optical potential W sub X, taken between Ju sub X plus times rho of K sub B on the left and right. Just below, the slide defines the ingredients. G sub X plus times rho of K sub B is the wave function in the X plus A channel. Rho of Co sub B is the source term, which means the X particle is not a free X, but comes together with the projectile A. It is given by the overlap of G sub B minus the interaction V, the full incoming state psi plus. For practical calculations, we also show the DWBA approximation, where psi plus is approximated by chi sub A plus times phi sub A. Let me introduce the code. Smoothie stands for Scattering Model of Optical Pauper-Serre Theory for Ikimura-Ostern-Vincent equations. On this slide, the key features read as follows. It is a modern Fortran implementation of the IA formalism and calculates non-elastic breakup cross-sections. It supports multiple optical potential models, and there is a web-based input generator for quick starts. Just below, the availability panel lists the website, smoothie.viewbuddy.com, notes that the project is open source under the MIT license, and confirms platform support on Linux, macOS, and Windows. That is exactly what Smoothie provides, a practical, open, and portable tool for inclusive break-em-up analysis. Because many of you will want to try it, the next slide is titled Installing Smoothie. Prerequisites are simple: a modern Fortran compiler, make and APACK or BLAS. Then follow the exact commands shown. Clone the public repository PREL. Change into Smoothie public. Copy make.ing.fortran to make.install. Change into the Smoothie folder and run make. Copy the built Mingerictacle one level up into test to Elthiel. Change into test and run the smoke test with /smoothie less than test.in. 2 quick notes from the slide. Ejectable leaves in smoothie, while sample emits are in test ALS. And if your LAPACK or BLAS libraries are not in default locations, update the paths in make.ing. After any rebuild, copy the freshly built binary back into test. Then rerun your sample cases. With prerequisites handled, we now peek under the hood. On the smoothie eclectical slide, the left panel lists 5 points: advanced AA formalism, Lagrange mesh matrix, Green's function approach, Intrin's purport, and HPC optimization. The right panel maps modules to their roles exactly as shown. General modules for precision, constants, systems, and channels. Mesh modules for numerical integration and Godot quadrature. Hot modules for Wood-Saxon, Kate Siratu AC Heightenine, and external potential files. QBUP modules for partial wave tools, including Coulomb functions, spherical harmonics, and Klebsch-Gordon coefficients. And CM to lab for the Centeroff mess to laboratory frame conversion. Now, the smoothie could file slide. Primary input is a Fortran namelist file, for example, test.in, passed via standard input. Core sections are 4, as listed on the slide: global, beam energy, angular grid, mesh controls, and DWB options like LLEB, the Tankerment, and DWB. System, particle fedenders, masses, charges, and spins name P, mast, and JP are shown. Outgoing Hauke the energy grid for the detected fragment, fields like EM-BEMN and ECM-BES. Potential half-U optical motor choices per channel, for example, p-type equals 41 to read 4.41. Smoothie echoes the parse name lists to 4.1. Compare it to your template to verify overrides. The suggested walkthrough is simple. Policy duplicate smoothie/test/test.indust, adjust reaction parameters in each bytecode, then run ./smoothie less than test.in. To make that concrete, the next slide shows the top half of the default test.in file from smoothie/test. We keep the NAMELIST header, and the rotating underlines key parameters like the radial mesh HCM and NR, and the angular coverage theta min and theta max. Please duplicate this template before editing. Very briefly, here is what each field means in the order they appear, with more detail in the manuscript. In global, HCM, the radial step size in femtometers, Lmax, the maximum orbital angular momentum, lab, the laboratory energy of the projectile in Make-A ligand bolts, theta min and theta max, the angular range for outputs in degrees, theta inc, the angular step, nx, the number of angular integration points, Rmax, the maximum radius, nr, the number of radial mesh points, and Lx max, the maximum orbital momentum allowed for the unobserved fragment channel. In system, the names, masses, charges, and spins of projectile, target, detected fragment, and unobserved fragment. The binding energy, BE, taken as the positive number for the bound pair. The orbital momentum of that pair, LBX. The number of radial nodes, and, when present, the spin coupling flag, SBX. In outgoing, ECMB mean and ECMB max, the energy window for the detected fragment in the center of mass system, and ECMBH, the energy step. In potential, KP1 identifies the channel, projectile, detected fragment, unobserved fragment, bound pair, or target valve. P-type selects the optical model family, and the subsequent symbols such as UV, AV, and RVIL or UW, AW, and RW, and the Coulomb radius, RC, are the standard depth, diffuseness, and radius parameters defined by that model. The second half of the example highlights the 5 required potential blocks exactly as they appear on the slide. KP1 equals Z, KP1 equals B, P1 equals X, PP1 equals PT, and KP1 equals T. For A, we show a Wood-Saxon set with depth, diffuseness, and radius parameters UV, AV, RV, and imaginary terms UW, AW, RW, as well as the Coulomb radius RC. For B, X, and T, the example uses the global set with p-type equals 4. For P, the bound pair, the example uses p-type equals 2 with its own UV and AV. At the end, there is a final sentinel line Hauck amperes and potential slash. Keep all 5 blocks and the sentinel, remove none. Copy the template, then edit the parameters you need. From inputs, we move to outputs. This slide, Smoothie Output Files, 1 of 2, lists the files by their Fortran unit numbers. 4.1 API local copy of the input namelist. 4.2 Hazel phase shifts for each incoming channel. 4.3 the complex asymmetrics of the incoming channel. 4.4 Haze the radial wave function for the projectile channel. 4.7 Enfing state wave function for the bound pair. 4.8 the channel coupling index table. 4.14 how the magnitude of the wave function in the unobserved fragment plus target channel resolved by orbital momentum. 4.19 how the cross-section distribution by total spin and parity. 4.20 L the cross-section distribution versus the channel index of the unobserved fragment. 4.21 the doubled efferential cross-section versus angle. 4.22 pints, the cross-section distribution versus outgoing energy. 4.23 and 24 Repe's partial cross-sections grouped by the orbital angular momenta of the detected and spectator fragments. All of these files are written next to your run directory, for example, smoothie/test, ready for plotting or post-processing. Now the second output slide. 4.30 Halsey, the potentials used in the calculation. 4.31 the imaginary potential W sub x of R sub x. 4.32 the parameters of the calculated potentials. 4.10 hone the radial part of the wave function for the detected fragment channel. 4.51 the same radial wave function reported on the calculation grid. 4.20 hone the regular component of the Green's function. 4.251 the irregular component of the Green's function. Depending on options, additional Fort files may be produced, following the same numbering pattern. Up to now, all cross-sections are in the center-off mass frame. For comparison with experiment, we rely on the cm to lab utility. Smoothie automatically writes m2lab.in after building cm to lab by running make in its directory. Execute ./m2lab/m2lab less than sem2lab.in from the test folder. That produces the lab frame observables labeled 4.910 and beyond, aligning our calculations with measured angular distributions. With the RUCMO in place, we now showcase 3 applications. The first is halo-induced reactions. Beryllium-11 on zinc-64 at 28.7 MeV. I use Smoothie to reproduce inclusive beryllium-10 production data, illustrating how halo structure influences breakup patterns. The slide displays the calculated versus experimental distributions from the Physics Letters B article. Application 3 turns to knockout reactions. On this slide, N-triggling breakup cases are shown Rundhauk. Oxygen-14 at 53 MeV on beryllium-9 and carbon-16 at 75 MeV on beryllium-9. Key results as listed. Agreement with experimental data. Validation of a fully quantum treatment against the iconal approximation and extraction of spectroscopic factors. A right panel shows the comparison plot. On the summary slide, I recap our central contributions. Smoothie delivers a full, fine iterange IAF implement, exposes a clear installation path, provides a robust input template, documents its outputs, and supports lab frame conversion. The tool is open source, well documented and validated against data. The acknowledgement slide. Collaborator, Antonio M. Moro, Upol Note de Sevilla. Funding support: the National Natural Science Foundation of China and the Fundamental Research Funds for the Central Universities. Thank you for your attention. Questions and discussions are welcome. For more information, Shavel the smoothie code smoothie.fewbody.com, our research group lutterdebjil.fewbody.com, and contact Jean Len at fewbuddy.com.